Okay, good day again to each and everyone who is watching right now. This will be problem number 2 for the truss structure. As you can see here on the free body diagram, we have here a truss system supported by a pin at point A and a roller at point E, with an applied load here at point H and point F equivalent to 140 kilonewtons at each point. We have here the measurements for A to H is 6, H to G is 6, and then G to F is 6, and F to E is also 6. And the unit for the length is obviously in the metric system, that's in meters. And the height for members D to F and B to H is equivalent to 4 meters. And the problem gave us some limiting factors that for a member that is under tension, the maximum allowable stress is only about 140 megapascals. And for any members that is in compression, we have a allowable stress equivalent to 100 megapascals. And the problem wants us to solve the least minimal cross-sectional area for these corresponding members CD, GD, and GF. So we have 3 members that we need to somewhat find their corresponding least minimal cross-sectional area. Means to say that this member, that's number 1, we have GD, which is this, and we have GF, which is this one at the bottom. So we have a maximum of 3. And if you are thinking that we are going to use the method of sections, then you are correct. But first, if we are trying to solve a truss system, structured system here, we must try to solve first the reactions of each support, because that is the component that is supporting the whole truss system. That's why it's really important that we need to find first the reactions of each support. But for me, since I'm going to focus only on the right side, because most of the required is at this portion of the truss system, we are here at the right portion of this truss. So that's why I'm only going to solve for the reaction here at E. I'm not going to solve anymore for A, because the only thing I need is the right portion of this whole structure. And if I'm going to do that, solving for the reactions here at point E, I'm going to use again the summation of moments at point A, because what I need is this reaction at E, or R sub E. And upon doing that, I need to do my summation of moments here at point A, so that I can cancel out the unknowns at point A. And the only force that is going to rotate is this 140s at point H and point F, and of course the reaction at E. So let's do that summation of moments at point A. Okay, don't forget about the free body diagram. So I'm just going to remove this, and let's proceed in solving. Summation of moments at point A. Okay. So we only have 3 forces that's going to rotate. So we have here summation of moments rotate clockwise is positive at point A equals to 0. So equals, let's look again here. We have 140 kilonewtons. We have the perpendicular distance equals to 6. So it's going to rotate clockwise, so it's positive. So 140 kilonewtons multiplied by 6. So it's positive. And then we have another 140 kilonewtons is about 6, 12, 18 meters away from point A. So plus 140 kilonewtons multiplied by the perpendicular distance equivalent to 6, 12, 18 meters. Let's retain first the sign. And last but not the least, we have R sub E, which is about 24 meters away from point A. So it's going to rotate counterclockwise, so that's why it's negative R sub E. multiplied by the perpendicular distance equals to 24. And the thing that we must do here is we need to isolate R sub e by transposing this to the other side. So from negative, it becomes positive. And for this one, we can just simply factor out 140 kilonewtons because that's the common factor for these two. And just simply add their distance. 18 plus 6 is equals to 24. So this one, R sub e multiplied by 24 is equals to, factor out 140 kilonewtons, and the 6 plus 18 is simply 24. And solving for R sub e, that is equivalent, cancel the 24s, so 140 kilonewtons going up. So if we go back here in our free body diagram, R sub e is acting upward, meaning to say that we have a positive answer for R sub e, means to say that our initial assumption that it is going up is correct, because the support here at the roller is receiving most of the forces that is being applied on the truss. So it's equivalent to 140 kilonewtons. And since we're going to apply the method of sections, I'm going to cut this truss system to a maximum of 3 members only. Since I'm only going to use the right portion, I'm going to do my sectioning at this portion. So this is section 1. So I'm going to use the right portion. So I'm just going to draw it here. So we have here, going like this. We have like this. And since this is the portion that we managed to cut our truss system, we have here CD, GD, and GF. So it goes like this. Just going to erase that. Let's assume that everything is in tension. Then for GD also, let's assume that it's also in tension, like that. And we also have for GF in tension. So this one is P sub CD. For this, P sub CD, P sub GD, P sub GD, and P sub GF. P sub GF. So we have 3, and don't forget that we have the reaction heat here at the R sub E equivalent to 140 kilonewtons. So it's going up 140 kN, and we have this applied load 140 kilonewtons going downward. This one is 6 meters, then going downward, equivalent to 140 kilonewtons. So this one is 140 kilonewtons. So this is our free body diagram for the right section of this cut here, 1-1. And this one is also 4 meters. And from here on, our task is to solve for these internal forces acting on members CD, members GD, and GF. So what would be our easiest approach in solving for these members? So what I'm going to do is that I'm going to apply again the summation of moments, but the question here is that where is my pivot point? No? That's the question. It depends on the problem itself. So let's assign first the points. We have here D and we have here E, so that we don't attain any confusions. We have F for this portion. Okay. So for me, what I'm going to do here is that I'm going to have my pivot point at point D. And the reason is that P sub CD and P sub GD will cancel out because this is the pivot point, obviously. And the only forces that will tend to rotate the structure is P sub GF and P and this R sub E, which is equivalent to 140 kilonewtons. Because this 140 here would just directly go down. No, it doesn't rotate. But GF has a perpendicular distance of 4, and this 140 kilonewtons acting at the support has a perpendicular distance equivalent to 6 meters. So for P sub GF is equals to 4, that's the perpendicular distance, and for 140 kilonewtons acting here at point E is 6 meters. So I'm going to use my summation of moments at point D. Just going to set boundaries at this. So summation of moments rotating clockwise is positive at point D is equals to 0. Okay, by doing that, is equals to P sub GF is going to rotate clockwise. P sub GF multiplied by the perpendicular distance equivalent to 4. So that's 4. And this also 140 kilonewtons. It's going to rotate counterclockwise, so it's going to be negative 140 kilonewtons multiplied by 6. Then isolating P sub GF, and then dividing both sides by 4. P sub GF is equals to 140 kilonewtons, 140 kilonewtons multiplied by 6 divided by 4. And then P sub GF is equivalent to approximately about 210 kilonewtons. So this one is 210 kilonewtons. Since we assume that it is in tension and we have a positive answer, means to say that this initial assumption is correct. So this one is in tension. Okay, so already managed to solve for one. And the next process here is to solve for either P sub CD and P sub GD. So that would be part 2 of this lecture.